be pretty common for us to have some quantity that we know that depends on x, but we don't know exactly how it depends on x. We don't have it explicitly spelled out. So if that's the case, we just know that y depends on x, and somebody tells us, well, what's the instantaneous rate of change of y with respect to x? This is my abbreviation for with respect to, by the way. If someone asks us about that, the most we can say is that, well, it's the tiny change in y over a tiny change in x, right? dy dx. We're kind of limited in how much we could tell you. Now, if someone came along and said, well, actually, y depends on x in this way, so they say specifically y is sine x, then we can say a little bit more, right? Because in this case, dy dx then would be the derivative of the cosine of the sine, which is the cosine. So that happens sometimes. Sometimes we'll have a function that's a blend of functions that are clearly depend on x, and other pieces that we're not sure exactly how they work. So here's an expression. It has x squared times y. We know that y depends on x, but we're not really told what function y is. Then we have x times the sine of that same function of x, and then minus that function of x squared. So if we want to find the derivative of that, so if we want to take the derivative with respect to x of this whole thing, then we'll just do the best that we can. First off, I have x squared. That's definitely a function of x, and I know that y depends on x somehow. So that's a product of two functions. So I'll take the derivative of the first, which with respect to x would be 2x, times the second. So plus the first, which is x squared, times the derivative of the second. Since I really don't know how y depends on x, the best I can do is to say, well, that's equal to dy dx. Now let's take the derivative of this piece. Again, we've got another product, right? We'll take the derivative of the first. The derivative of x with respect to x is 1, times the second, plus the first, which is x, times the derivative of the second. Now this requires the chain rule. We've got this function of x inside another function, so we take the derivative of the outside, we plug in the inside, and then we multiply by the derivative of the inside. Finally, I need to take the derivative of this y squared. Now this is a case for the generalized power rule, because this y is some function of x. I'm not sure what function, but I know it's a function of x. And the generalized power rule says that the power is going to come down. You're going to have the function of 1 power less, which 2 minus 1 is 1, so we just have y, times the derivative of the inside, which is dy dx. So we have a blend of things we were able to take the derivative of, and things where we just had to say, well, dy dx, whatever it is. This is pretty important when you have a function that defines y as a function of x implicitly. So here's a simple example of an implicit function. X squared plus y squared equals 4. This equation creates a relationship between x and y. So I can see that since x squared plus y squared always has to equal 4, if I have some solution to this equation, I change x slightly, then I'm going to have to change y in order to compensate so that this is still equal to 4. So definitely y depends on x, but it's not spelled out. It's actually kind of folded in to the problem here. So we have an implicit function. This plic here is like in multiply. It's to fold over, and this im means to fold it in. So this is sort of an in-folded function. By that we mean that y is an implicit function of x. We mean that the dependence between x and y is not spelled out. Now in this case it would be easy to make it explicit by solving for y. So we have y would be plus or minus the square root of 4 minus x squared, but now y is an explicit function of x. So we have it spelled out, right? This is folded out, so everything's shown. How do you get y? Well, you do this to it, and that will give you the y. Now, in this particular case, I was careful to do the plus or minus. You might recognize, actually, that this is the equation of a circle of radius 2 centered at the origin. And so is this. It's just written as a function. If you use the plus sign, you get the values where y is positive. That draws the top half of the circle. And if you use the minus sign, you get the values of the circle where y is negative. That's the bottom half of this circle of radius 2 centered at the origin. So this is a way of kind of writing two functions together in a single function. All right, so if we wanted to find dy dx, we have two choices. If it's an implicit function, what we could do, since x squared plus y squared is equal to 4, if we look at how does the left-hand side change with x, that should be equal to how the right-hand side changes with x, because this equation always has, these two things always have to be the same. X squared plus y squared has to be 4. Well, so I'm taking the derivative of both sides with respect to x. The derivative of a constant is 0 over here. Now the derivative of x squared plus y squared, the derivative of x squared with respect to x is 2x. Here we have a function of x raised to a power, so the generalized power rule says the power comes down, you get the function to 1 power less, but then you have to multiply by the derivative of the inside function. So you might ask, well, how come I didn't write dx after this one, right? After all, x is a function of x, so the 2 should come down, you should get the function to 1 power less, and then multiply by the derivative of the inside. But of course, dx, the slope of a function whose slope is 1 is obviously 1, right? So I don't have to write it in that case. I'll just leave it off. Now that I've taken the derivative, I can go ahead and solve for dy dx. That's what I want to find here. How does y change with x? So if I pull over this 2x that doesn't have a dy dx in it, then I have some of the things that have dy dx in there. I'll just divide both sides by 2y. So if I divide the left by 2y and the right by 2y, I find that dy dx, the rate of change of y with respect to x, is negative x over y. Alright, now I could have done the same thing by first writing it as an explicit function. In order to take the derivative, I'll think of that square root as a power so that I can apply the generalized power rule, which would say that dy dx is going to be plus or minus. Bring the power down. You'll have the inside function to 1 power less. 1 less than 1/2 is negative 1/2. Times the derivative of the inside. Well, the derivative of 4 is 0, and the derivative of negative x squared is negative 2x. I can see that 2 cancels that 2. And I could write this as negative x over either plus or minus the square root of 4 minus x squared. What I've done was to say that this negative 1/2 could go downstairs and be a positive power, and something to the positive 1/2 is just a square root. So I get this expression. Notice that in this case, when I had y as an explicit function of x, then dy dx ends up being an explicit function of x. But when I had it implicitly, dy dx ends up depending on both x and y. So that's kind of the trade-off. You might think, well, it's easier to take the derivative without solving for y. You could also solve for y, and that might be a little bit harder, but at least it's a function of x. Here it's a function of x and y. However, you can see that these really are the same thing, because once we've taken the trouble to solve for y, we can see that what we have down here is just y. So this is negative x over y. Either way, we got the same answer. Whether we left it as an implicit function and then solved for dy dx, or whether we made it explicit and then found dy dx, the result is really the same number. This is a pretty handy technique. It can come up whenever it's difficult to solve for your variable. Here's a case. Now, you could solve for y. However, it would require using the quadratic formula, involve some not so fun looking square roots. So instead of doing that, I'm just going to differentiate implicitly. The first step is to take the derivative. So if the task here, I should be giving you a task. The task is to find dy dx. So if you want to find dy dx, then just take the derivative of both sides with respect to x. After all, we're told that both sides are the same thing. So whether I take the derivative left or the derivative right, I should get the same thing. Now the derivative of 7 with respect to x, of course 7 is constant, so that derivative is 0. Over here, the derivative of x squared with respect to x is 2x. This is a product of a function of x times another function of x, so I get the derivative of the first, so dx dx, right, times the second, plus the first, which is x, times the derivative of y squared, which is 2y dy dx. And then the derivative of negative y with respect to x would just be negative dy dx. Now my plan is to find dy dx. Notice that dx dx is 1, so I really don't need to write that. What I want to do, if dy dx appears in multiple places, let me get the terms that have dy dx on one side, the terms that don't on the other side. So the ones that do have dy dx are these two. We have x times 2y, so I'll write that as 2xy, times dy dx minus dy dx equals, if I pull these over, I'll have negative 2x and negative y squared. Now here's a little trick. You've probably seen it before. I have dy dx multiplying 2xy and also multiplying negative 1. So why don't I factor it out? And then I'll have 2xy minus 1 times dy dx. Now, if you're not sure about that, just distribute back in and make sure it's the same thing, right? If I take dy dx times 2xy, I get that. When I take dy dx times negative 1, I get negative dy dx. These must be the same thing, because when I distribute, I get back to where I was. Now, the last step, now that I have something multiplying dy dx, I can get dy dx just by dividing both sides by that. So I have minus 2x minus y squared all over 2xy minus 1. Okay, I could even maybe pull this negative out of both of these. If I factor out the negative, that becomes positive. Just write the negative out in front. With 2x plus y squared on top and 2xy minus 1 down below. I found the derivative of y with respect to x. I never had to solve for y, even though in this case I could have done it. It wouldn't have been fun. I never had to solve for y. I found the derivative. The only disadvantage is the derivative depends on not just x, but also on y. So if you want to find the slope of this function at a particular location, not only do you need the x value, you need to find the y value to go along with it.